right, so let me put this here. Okay, so I'm gonna ask like, who would like to do this one here? I'll do this one. Who would like to do this one? Come on, volunteer. Okay, Max. Okay, so Max, you'll be like this one. Hold on a second. Don't do anything yet. All right, so Max. All right. Who? Okay, who would like to do this one here? Aditya? Yeah. Okay, so Aditya. All right, so Aditya. All right, so we'll do this, and then who would like to do this one right here? Leo? Okay, so Leo C. All right. All right, so Max, so try like this one. So you can go and annotate. Just do this one here, all right? And do your best here. So that was an application of write-in rule number 3. FBI agent. All right. Okay. All right. All right. Good. All right. So let's look at this here. So, all right. So outside of magnet, magnetic field always goes from north to south. That's very good. All right. So if I do this here, let me see here. The current is going in. So my thumb is FBI. My thumb is in. The magnetic feels like this. I'm breaking my wrist. And my middle finger is this way. That's correct. So you're absolutely correct. Excellent. So let me do like this one here. So this one, so we know that this is going to be north and this is going to be south, because outside of magnetic field goes from north to south. The current is coming out, so it's coming out towards me, right? Towards me, and the magnetic field is going down, right? So my going down like this, so the force will be as such. Is that okay? Good? Okay. All right, so let's look at this one, the Aditya. I'll do A. Are you doing it? Aditya? Yeah, okay. All right, so you say that the current is coming out of the page, right? Okay, so let's look at this here. Like here, I can, in which direction is your magnetic field going, Aditya? It's going from north to south or south to, because there's a little kink here. Aditya, in which direction is your magnetic field? Oh, come on, don't just talk. Oh, chat. Hey, chat. It's not letting me annotate. Oh, that's too bad. Well, you did annotate something. Send you? So let me see here. You should be able to annotate. Wow. Anyway. Okay. All right. Good. Yes. So the north, yeah, that's correct. So it goes like this, right? And your magnetic field, your force, which is like this. So it's coming. The thumb is going towards you. So you're correct. So the current is coming out of the page. Okay. So let me do this one here. All right, so if I do this one, so magnetic field goes from north to south in a magnet. So this is north, this is south. So magnetic field is down. The force is like this. So and the thumb here is coming towards me, out. So it's going to be out as well. It's going to be a dot. You good? Okay, so Leo. So do this one, Leo. See, I think. Yeah, I know it's hard to. Okay. All right. Okay. So you said that up is north. Okay. That's the okay. So this is the magnetic field. The magnetic field goes. No, you don't have to do more. I don't know what that is. All right, so you needed to find like the north and south the magnetic field. So once again, like the force is this way. The current is going into the page. So if I'm doing this, going into the page, and the magnetic field is going down. So that's correct. That's correct. So magnetic field is going down. This is north. This is south. Absolutely correct. So the second one here. The force going this way. The current is I. The current is coming towards me. So magnetic field is pointing up. So the magnetic field is pointing up. So it'll be like this. So that's the magnetic field right here, and it always goes from north to south. So this is north and this is south. All right. Very good. Okay, this one. Does anyone want to tell me, like, in which direction this one rotates? Oh, Jason. Jason, your mic mute. Your mic is on. So there we go, Jason. No. You know how to do wood, Jason.
Yeah.
Which direction does it move here? Is the upper part here? Does it move towards you or away from you?
Upper part is moving away from me.
Okay, so let's look at this here. All right, so let's look at the current. So the current here is going from high to low. So it's going like this, right? So that's the current here. The magnetic field is going down like that. So that's the magnetic field right here, outside the magnet. So let's figure out the force on the top portion. So the force on the top portion, so the current is going this way. Now I'm going to break my magnetic field is going down, and my middle finger here is going into the page. So there'll be a force on the upper portion will be into the page. There you go. So that's the force right here. And you can sort of see here that you can see as well that on the bottom, current is this way, magnetic field is like this. So you can see here the force is coming out of the page. So on the bottom here, it's coming out of the page. So the overall effect is the bottom one, the upper portion of the arrow is going away from you, and the bottom is going towards you, right? So it goes like this, all right? So I don't remember what you said, Jason, but anyway, so it goes like this. Goes like this. All right, you good? Okay, so for this one here, so it goes like that for the current, high to low, the magnetic field. Outside the magnet is always from north to south, so it goes like this. All right, so if you look at the upper, yes, Madhav.
So shouldn't it go the other way? Because the top is being pushed towards.
Yeah, that's it. That's it. That's my okay. That's my axis here. Okay, it goes
Yeah,
like this.
I think it should rotate the other way. Fine.
No,
I see.
no, it rotates like this. It rotates like the top part is moving away from you, and the bottom part is going towards you. All right, so rotate like this. Okay, so yeah, so the current on the top portion goes this way, the magnetic field this way. So the force is also inside. It's also away from you. All right. So if you look at this loop here, if you look at this loop, so it moves also this way. All right. So it moves also the same direction as above. Right. All right, so it moves like this. Are we good? Okay, the last one here, well, you just follow the current here. So let's look at this here. So you identify the positive, the negative side of the, or I should say the higher and the lower electrical potential side of the battery. So current will go like this. All right, so go through the brush here. We'll go through this. We'll go through the coil. All right, we'll go like this, and then go this. There you go. Come back to the other side of the split ring commutator, and then finally go to this. All right. So that's the direction of the current. So the current of the coil is going like this. If you write in rule number 2, so you wrap the coil in the direction of the conventional current. So the thumb points towards the north side of this electromagnet. So this is north, this is south. So of course here you have north and south. So there'll be an attraction. So there'll be a force of attraction this way. There'll be a force of attraction, magnetic force this way. So therefore, this coil is moving this way, right? You good? Questions? Yeah. Yeah, I apologize, Madav. I don't check my K-12 account all the time. So I know you invited me for something, but apologize for this. All right. All right. So if you have no other question, let's continue here. All right. So let me clear the annotation. So clear. Where's the clear? Clear all drawings. There we go. All right. Oops. Okay. Good. All right, so we look at this DC motor. Okay, so next topic we're going to cover is the electromagnetic induction, Faraday's principle. Okay, so the first thing I want you to do is I want you to cross out this. There we go. So cross all of this. Okay. All right. So what is found here is found the following. It's found that when you move a magnet, you create an electrical field. Okay, so when a magnet moves, it creates an electrical field. So if there's a wire in the vicinity, this wire will sort of sense this electrical field, and the electrons or the charge will be set in motion. So in other words, here, so if this is a wire right here, and this is a magnet. If I move my magnet, I wish I could be at school. I would show you this phenomenon. But if I move this magnet, you would see current being produced in the wire without touching. And remember here from grade 9, to cause something to happen without touching, this is called induction. To induce is to cause something to happen without touching. All right. So this is called electromagnetic induction. By moving a magnet, you are causing a current to flow in a wire, even though like the magnet and the wire are not in contact with each other. And this is what's discovered by Faraday. So this is called Faraday's principle, electromagnetic induction. Now, if you want to, so bear with me here. I'll just go and grab here. There you go. You don't have to write this down, guys. If you want, you can, but you don't have to write this down. So if I look at a magnet, so let's say here, this is a little magnet. This is north and south. And I have the magnetic field. Right, so that's the magnetic field here. Okay, so let's look at a point right here. So let's look at a point right there. So at this point here, the magnetic field is going in this direction and has a certain magnitude. All right, so has a certain magnitude. Now, if I move the magnet, so if I move the magnet, all right, so let me move the magnet right here. If I move this magnet, of course, the magnetic field will come along with it, right? So the magnetic field will come along. So let's do this here. All right, it's not really well done on the other side, but that's okay. What I want you to understand here, I want you to understand that now at this exact point here, at this exact point right here, the magnetic field has changed in both direction and magnitude. So it's farther away, so the magnitude is less, and the magnetic field is somehow like going, whoops, going somehow like this here, a little bit. All right, okay. So this is the final, this is the initial right here. So what happens here is that at any location, I did it at one point in space, but at any point in space, when you move a magnet, the magnetic field will change in either direction or magnitude. And whenever there's a change in magnetic field, it creates an electrical field. So if I had like a little charge right here, if I had a little charge, well, at any point in case, and as a matter of fact, but if I had a little charge right here, electrical charge, it will start like moving. It will start responding because there's an electrical field that will be generated. All right. So this is what it means here. This is what it means. Where am I? There we go. So this is where it means. So when the magnet is moving, there's a change in magnetic field, and the change in magnetic field will produce an electrical field. Okay. All right. So here's we have a magnet. All right. It's a little magnet here, and we have a coil. The coil is open. You can make it open if you want. Doesn't really matter here. Oh, you can close it. Let's close it. All right, there we go. We'll close it. So if I move the magnet, as I move the magnet, there'll be an electrical field generated everywhere in space. If there's a wire, it will sort of set the charges into motion because it's responding to an electrical field. So there'll be an induced current. You can see here the induced current right here. Okay. Now, if you use a voltmeter and measure if it moves, there must be a difference in electrical potential. Remember, right? Electrical current will not move if there's no difference in electrical potential, if there's no voltage across. So if you were to do this and put a voltmeter, this is a galvanometer, but it's a voltmeter too. So you put a galvanometer here, voltmeter across. When you move the magnet, you're going to see a voltage being produced. Okay. So there'll be an induced electrical potential difference, an induced current and an induced voltage. And of course, like the two are related by Ohm's law. If it's a wire that follows like Ohm's law, you'll have the relationship here. So the induced voltage is equal to resistance times the induced current, right? And this is called electromagnetic induction. That's pretty neat, all right? And I wish we could be in class here and I would sort of show you. I would sort of move a magnet. I would have like a little device here I would have a solenoid, and then I would put like a voltmeter across, and you would definitely see voltage being produced as I move the magnet. What you would see also, now you have to use imagination here, you would see that if I move this magnet even faster, the induced voltage is greater, or the induced current is greater. You would also have noticed here that if I remove the magnet away, the direction of the current reverses, and the direction of voltage also reverses. That's what you would see if I were to do this in class. Okay, Lenz's law. Lenz's law tells you, gives you a prediction of the direction of the induced current as you move your magnet. Oh, by the way, it's not the magnet moving that is important. It's the relative velocity of the two. So I could have the magnet stationary, and I could sort of move this. I would sort of have like the same effect here, right? I could sort of have this magnet not moving, and moving the coil towards the magnet, I would sort of see an induced current as well. Okay. If I make the magnet and the coil move at the same speed in such a way that there's no relative motion, there won't be any induced current. Okay. All right. So Lenz's law helps you like to predict the direction of the induced current, given like in which way the magnet moves or the relative motion of each. Okay. So here I'm going to read this. Probably you're not going to understand much of what it says. All right. But I'll read them. So the magnetic field of an induced current. So you remember here when there's a current, there's a magnetic field and it's produced. So when there's an induced current, there'll be a magnetic field produced around the wire. This is called the induced magnetic field. So the magnetic field of an induced current always opposes the change in magnetic field that is causing the induced current. All right. So we'll come back to this a bit later. Let's look at the second definition here. The direction of the induced current is such as to create a magnetic field that will oppose the motion that creates a change in magnetic field in the first place, responsible for the induction. Okay, so let's look at this here. All right, if I move the magnet, this magnet here, towards this coil, the induced current will be going in this direction in the coil. Why would it not go in the other direction? Why would the induced current not going in the other direction? Well, this is why it doesn't happen. This is why that doesn't happen. Imagine here. So imagine here that okay. So if the induced current going like this, if you use right-hand rule number 2, you figure out here that this is south and this is north. Now, this is an electromagnet. So south and north attracts. So here is the thing here. If I have this little magnet here, and then I just give a tiny push, just tiny push, so tiny bit of kinetic energy, towards this this coil here. What happens here? Well, if the induced current were to go this way, there will be a south pole here, and this magnet will go even faster. Well, if it goes faster, the induced current will be even greater. If it is greater, then the magnetic field here produced by this coil will be even greater. So the magnetic force on the magnet will be even greater. So what will happen here is that out of a very tiny push here, you have enormous amount of kinetic energy. All right? You have enormous amount of kinetic energy. There won't be like any problem with energy anymore because you just give a little push, and this magnet will keep on accelerating, speeding up. And then you're gonna have like enormous amount of kinetic energy for nothing, right? Just a little push. So of course that cannot happen because conservation of energy would be violated. So this is what happens here. This cannot happen here this is a violation of conservation of energy. What happened here is this. All right. So if I push the magnet toward this coil, the induced current will be in such a direction. So the current will be in such a direction, right? And to create a magnetic field, so this this wire here, this coil will create a magnetic field. If you use right-hand rule number 2, you find here this is north. And then what happens here is that when I push this, I will feel a resistance. Because like there's a repulsion here, right? So if I were in space and I would sort of give a little push here to this magnet here, what happens here is eventually the magnet will come to a stop. Okay. Wires don't like to have their current change in them. Okay. You can think of it as inertia. Remember inertia? Resistance of an object to having its state of motion being changed, its natural state of motion being changed. So if an object goes at constant velocity, it wants to keep going at this same constant velocity unless an external force acts on it. Well, you have this kind of the same thing for wires also. Wires when there's a current running through them, wires don't like to have their current being changed. They will resist. So if there were no current to begin with, they will want to go back to nothing, no current. Now, when you do this here, when you move the magnet, you're forcing an induced current. The wire doesn't like it. It will sort of be going in such a direction, in such a way as to bring this to a stop. All right? So this is Lenz's law. So direction of the induced current will be in such a way as to create a magnetic field that will oppose the motion that creates the change in magnetic field. Remember here, what has caused the induced current is the fact that I'm moving a magnet. And as I'm moving a magnet, I'm changing the magnetic field around. And as a change in magnetic field will create an electrical field. An electrical field will set like a current in a wire. The wire doesn't like it, it will oppose it. Okay? All right, so questions. All right, so let's do a example here. If you want, you can write it down. It doesn't really matter here, but okay, so. All right, so let's say here you have this coil right there. And let's say that you are moving this coil away. So I will always put an arrow with a little V here to tell you in which object, first of all, is moving, and this one is moving away. I'm taking this, I'm moving this, this magnet away. Now, what I'm doing here is I'm changing magnetic field in the surrounding area here. A change in magnetic field will create an electrical field. If there's wire, it will set up an induced current in the wire. Now, the wire doesn't like it. There's no current in it. It wants to have no current. So what it will do here, it will try to oppose my moving it. It will try like to keep the magnet from moving, because this is what has caused the induced current. It doesn't like it. So in order for it to resist my pulling the magnet to the left, what it will try to do, it will try to create a north pole here. Because by creating a north pole here, there'll be an attraction, right? There'll be an attraction here that will sort of resist my pulling it to the left. So if it creates north here, this is south. Now you use right-hand rule number 2. So north is this way. So the induced current will go in this direction. That okay? So once again, Lenz's law will tell you here that the direction of the induced current is in such a way as to prevent what has caused the change in magnetic field in the first place to occur. You'll try to bring this to a stop. Very good. So if I move this this magnet away, the induced current will be in this direction. Okay. Okay. So let's do another example here. So let's say here, it's your coil. Actually, I should have closed it. Okay. If I open it, there'll be a difference in potential across, but there won't be any current because the resistance is infinite, right? So if it's an open circuit, all right. Okay, so in this case, let's assume that I'm moving the coil away. So once again, as I said here, what's important is the relative motion of both. If I move this away, when I move this away, the wire here encounters like different intensity magnetic field. So magnetic field produced by this magnet here is of course fixed, But as I move the wire will experience a difference in magnetic field intensity and also direction, right? So a change in magnetic field will produce an electrical field. So there'll be an induced current here. Now, the wire is not happy about this. I'm pulling this wire, this coil away. It will try to resist my pulling it to the right. In order to resist it, what it needs to do, it needs to create a south pole here so that there'll be a force, magnetic force right here, opposing my pulling it to the right, all right? So opposing my pulling it to the right. It must be a force of resistance, right? So if this one is south and this one, so this one will be, of course, north. Now you use right-hand rule number 2. So your thumb is in this direction. So the current is going the coil this way, all right? So the induced current will be in this direction. Okay? We're good? So the direction of the induced current in such a way as to oppose you moving the magnet of the coil, right? Yes, madame.
When you have the currents oppose the movement
Yeah.
and the magnetic field is generated, is the magnetic field generated, the force like of attraction, is that equal to the kinetic force of you moving the object?
Okay, hold on a second. So this one here will create a magnetic field. Is that what you're talking here? So we'll create a magnetic field, and it will sort of try to offset any changes in magnetic field. Just wait for tomorrow, okay? I'm gonna sort of talk about, this is like the second one here, all right? So this one here. So I will talk about this tomorrow, okay? Okay, so just be patient here, okay? All right, so let's do another one here. Oops. Okay, this is not very good here. I mean, so do a better job here. Okay, let me use this here. Woo! Ah, it's not any better, but anyway. There you go. All right, so let's suppose here that the current is going this way. Now, what you want to do is you want to tell me, is the magnet moving this way or is it moving that way? All right, so which way am I moving this magnet here? Well, once again, so this is the induced current right here. So using right-hand rule number 2, you can figure out here. So you wrapped like the coil in the direction of the conventional current. So north is pointing this way. So that's going to be north. That's going to be south. Remember here, you should sort of feel the force of resistance, right? So this one here is south pole. So of course here, what happens here is that you're actually moving this magnet towards the coil because there will be a force of repulsion resisting you, right? It cannot be, you're not pulling it this way, because if you're pulling this way, then you're helping, right? And then conservation of energy will be violated here, right? So you give a little push this way to this magnet, and then it would keep on having more and more kinetic energy. Yes, Max.
Wait, how come? Wait, but don't opposite poles attract and like poles?
Yeah, this one is, there's repulsion here, right? The south and south.
Yeah.
Yeah. So when you're forcing this towards it, right? You're forcing the magnet to the right, and you should feel a force of resistance. The only force of resistance, and the force of resistance comes because there's a south and south. So there'll be a repulsion, right? You're pushing this, right? So this is your applied force here. You're pushing this in, right? But because of south and south, there'll be a magnetic force opposing you. All right. So there'll be a magnetic force here opposing. U. Is that okay?
Wait, so so the so the V on the top is you
Like,
pushing it
the
towards
question was like, in which direction am I moving this magnet? Am I moving towards the coil or away from the coil? So that was the question.
So when you move it, it's always in the move. It's always in the direction of how it repels.
It's always in the direction how it repels. I'm not so
Uh,
sure if I
uh,
understand you
sorry,
here
so-
because
sorry,
magnetic force is this way,
sorry.
right?
So the direction in which you pull like so the direction of the motion of the magnet is dependent upon which direction it resists, right?
Well, it depends on like which is it north here, is it south? It depends on right. So it depends on this, right? But the key point here is that you should always have a resisting. You should always have like a force resisting you moving the magnet or the coil,
Oh, okay.
and that will sort of determine like so you'll be able to sort of find out in which direction you're moving the magnet or the coil.
Okay.
Okay.
Great.
All right. Good. All right. So let's go back to this here. So that's Lenz's law. And once again, I wish I had you had this at school here. I would sort of show you this with demos. Okay. So I'm going to stop sharing because it's lagging. Let me sort of share this again. Okay, so not everyone is here. There's 3 students missing. There we go. Okay, so now we're going to talk about ways to generate electricity. Well, you can see this, and this is why like Faraday's law was so important. Faraday's law is a way for you to generate electricity just by moving a magnet or by moving a coil relative to each other, and this is how electricity is produced at the electrical plant. This is all how it is produced. Okay. So Faraday's principle provides a mean by which electricity can be generated. So remember here what I said. What matters is the relative motion between the two. It doesn't really matter if you move the magnet and the coil is fixed, or you move the coil and the magnet is fixed. As long as there's a relative motion between the two, you're going to have an induced current, a current being generated. Okay, so now we're going to talk about alternating current. So alternating current is different from direct current. Direct current means that the current goes only in one direction. So in a battery, you have the current going only in one direction. Up, there we go. Timothy is late. Direct current, as produced by batteries or photovoltaic cells also, the current goes in only one direction. That doesn't mean the current stays constant, but it goes in only one direction. AC is the current goes one way and then reverses, and then periodically does that. So what you get out of your outlet is AC current. So the current, so when you plug this, right, the current in your device goes one way and then reverses direction. Okay? And you're going to sort of find why this is in a second. Okay, so in North America, the cycle is 60 hertz. All right, so it goes one way, and 120th of a second later, it reverses direction. 120th of a second later, it goes back to the original direction, and so on. So it's 60 hertz. In Europe, it's 50 hertz instead. Okay, so a generator is a device it's an electrical device that converts mechanical energy, rotational energy, into electrical energy. So a generator is really the inverse of a motor, because a motor takes in electrical energy, converts this into mechanical energy, right? And once again, if we were at school, I would sort of show you that a motor can also work as a generator, right? Okay, so an AC, we're going to look at an AC generator, and perhaps later we're going to, I don't know, today or tomorrow, we'll look at the DC generator. We'll see if we have time. Okay, so an AC generator is a device that generates, of course, alternating current. It's made up of three general parts. It consists of an armature. So an armature is nothing else but a coil of wire, like your coils, right? Or like little coils like this around the permeable core, so around the iron core, or and so on. A field magnet, just like a motor, remember, a field magnet, the permanent magnet surrounding the spinning armature. And instead of a direct split ring commutator, you have what is called a slip ring, which is different from a split ring. Okay. So now, it's lagging here, but it's coming. So okay, so pay close attention. Wow, it's so lagging. Still there. Okay, let me stop sharing here again. Poor little computer. There we go. Okay. So pay close attention to this. This is your coil here. They show only like one loop, but there's many loop here. According to Ryan rule number 2, so current in the coil is going this way. So this is the north side of the coil. This is south side of the coil. You've got the field magnet right here. And you have wires here that is connected to a voltmeter, ammeter, doesn't really matter. Now, generator is a source, right? So it generates electricity, right? You are turning it. So here they show you the direction in which you make this coil turn, okay? So you turn like clockwise. Now, this here are the brush. Remember the same brush as before. So they make sure that they connect the external circuit here to your generator. But instead of being a slip ring commutator, you have a split ring. You have a slip ring. So what happens here is this: you have a cylinder here, which is made of an insulator, plastic, wood, probably plastic for the most part. And on each side here, you have a fine layer of metal all around, all around. You have one at the top, one at the bottom. And one of the carbon brush here is always connected to the upper part. And the lower brush here is always connected to the other side of the slip ring, okay? All right, so let's take this off here. So what we're doing here is I am turning this. Now, as I'm turning the wire sees a varying magnetic field around, right? So magnetic field here is fixed in this case. It goes from north to south this way, right? But as the wire like goes in space, right, as I turn it, it experiences a changing magnetic field in both magnitude and direction. And this will create a electrical field. An electrical field, so if there's a wire, it will set a current, it will induce a current. And this is exactly what happens here. All right, so I am turning this. As I'm turning this, there will be an induced current. And the direction of the induced current will be in such a way as to oppose my turning it. All right, so I am turning it clockwise. All right, so this is what I'm doing here. I'm turning it clockwise. All right, so here, let me see here. It's the applied force here, right? Whoops. The applied force. Now, Lenz law tells you there should be something that opposes me, right? Of course, when I turn this clockwise, there should be north here, so that there's an attraction keeping me from turning it. You're resisting me from turning it clockwise, all right? All right, so let me put this here. All right, so there'll be a magnetic force here, right? That's the magnetic force opposing, all right? So I'll have an induced current, and so let's say here the induced current is going in, it's going in the coil and then goes into the external circuit, and this is the direction of the current flow, All right, everyone follows? Okay, and so here, so it will be like about here. So here, this could be the induced voltage, or it could be the induced current. Doesn't really matter here. It could be the voltmeter, a voltage here, or the current, right? So it's around here at the moment. Now, as I turn it, so I keep on turning. Now, as I go past the vertical, the current, the induced current is still in the same direction, because once again, I'm turning it like clockwise. It should be something resisting me. Well, here, this is north and this is north, so there'll be a force of repulsion where the magnetic force will oppose my turning it clockwise. So everything is okay. So this side here doesn't, like the pole here doesn't change, right? It's still north, so the current in the coil is still going the same direction, right? So this is going the same direction. So I'm about like perhaps like here. Okay, oh, actually, oh no. Yeah, it's not a very good diagram here. Well, they were doing like something like this here. Okay, so about here, like I'm here. Anyway, now, when I come to horizontal, there's no current. Okay, there's no induced current. I'm not going to tell you why, but there's no induced current here. When I keep on going, turning this, if the current in the coil were going the same direction, right, then this still would be north. If this is north, if this were north, don't write this down here, but if this were north, here, then there will be a force of repulsion helping me turning it clockwise. But Lenz law prevent this. There should be a force of resistance. So what happens here, in order to have a force of resistance, despite the fact that I'm applying a force this way, is that I need to have a south pole appearing here, right? So now that there'll be a force of attraction, magnetic force, opposing me, right? I'm still pulling this way, right? So there should be, so the current has to, so the pole has to change here. If the pole has to change, then the current in the coil has to change direction. But since this brush here is always connected to the same side here, it's always connected to the same side here, what will happen here is that the current in the external circuit will change direction, right? So here it was going this way, and now it's going this way. So here it's going one way, the voltage is one way, and then later it's going the other direction. And this is why what you create alternating current. By turning this, because of Lenz's law, the current in the coil will change direction periodically. And since the slip ring commutator here makes sure that the external circuit is always connected to the same side of the coil, so what happens here is as the current changes in the coil, so will the direction of the current in the external circuit here. Is that okay? All right, so now why does it vary? Why does the current increases and then decreases? All right, so we understand now why the current goes one way and the current goes the other way, but why does it increase, decrease, increase in the other direction, decrease, and so on? Well, think of it as this. We'll talk about this a bit more in details yesterday, but you remember when we change a magnetic field, it creates an electrical field. If I have a magnet and I pull even like faster, the magnetic field will change even faster. And if it changed very, very fast, if the rate at which magnetic field changes very fast in either direction of magnitude, the electrical field induced will be even greater. Okay, so what happens here is that when the coil is right here, when the coil is at the vertical, this is where the coil sees the greater change in magnetic field. When the coil is horizontal here, it hardly sees a change in magnetic field. So when the coil is horizontal here, the current is zero. When the coil is vertical, this is where it sees the greatest change in magnetic field. This is why the induced current is greater, or the induced potential is greater. It's like this here, guys. All right. I have my hand here going at constant speed. If you look from above, going constant speed. If I ask you, like, where does it feel it goes faster? Right? Well, you're going to say it seems to go faster like here, right? Instead of here. Here, like, from your point of view, it doesn't seem to move much, right? But here, it moves a lot. So that's the same idea here, okay? That's the same idea. So what you do here with an AC generator is you actually generating AC current. And this is because of Lenz's law, all right? So this is a slip ring commutator. Sorry, a slip ring, that's correct, slip ring commutator. Okay, any questions? All right. Just let's say here, if I want the current to go in only one direction, I don't want the current to reverse. Can you tell me here what pieces of equipment I should change in my generator? Does anyone, can anyone guess? My question here is as follows, all right? I want to generate I want to have a DC generator. So a generator that creates current that goes in only one direction. What piece of equipment do you think I should change from an AC generator to turn this into a DC generator? Does anyone know? Anyone guess? It's only one piece that you need to change. No? No, come on. No one knows? Oh, a bit disappointed. Nah, just raise your hand. Stop chatting. Okay, Joe, can you talk? Can you talk, Joe, or no? Because I know, like, Joe had a bit of a problem. Not on this one. Okay. All right. So what we do is a slip ring. You will replace a slip ring with what? What do you think? What would you, two parts? You would replace two parts, or would you replace one part? You were on the right track here. You would replace one part. Okay, slip ring is fine. So you replace a slip ring. We'll replace a slip ring with what? One part, two separate parts. Okay. Kind of know where you're going a little bit. Okay, so anyone know here? Like, okay, so you need to replace a slip ring with something else. What do you think, guys, you would replace a slip ring with? Anyone? No one? To replace a slip ring with a what? Come on. Someone. It's something that you've come across. Last lecture. I'm being patient. There you go. There's it. Stephen, do you know? Ah, not Stephen. Timothy, you can't. Okay, Stephen, yeah?
I said no.
No. Okay, Timothy, you came late. All right, unmute. So,
Would you need a gap in the slip ring?
Okay, all right. That's good. Okay, well, what you would do here is you would replace a slip ring commutator with a split ring. It's lagging. I can still see my. You would replace it with a slip ring. So what happens here is that you have like two effects. So what happens here is that as you turn, you remember the current in the coil will reverse direction, but if you allow like the brush here to be in contact with the other part of the circuit, it's like two reversal in a row, and it will sort of give you like the same thing. It'll make sure that the current, well, of course you have to go at you have to set this up so that the frequency at which you turn this matches the frequency here, like of the brush here, right? But that's what you do. All right, so you would replace a slip ring commutator with split ring commutator in such a way that when the current in the coil reverses, by the time it reverses, the carbon brush, like this one here, is in contact with the other side of the coil. So in such a way here that the current in the external circuit goes in the same direction. So if you have, so this is an AC generator here. But if you were to replace a slip ring with a split ring commutator, then you would create a DC generator. All right, so let's put this here. All right. So a DC generator has a split ring commutator. Split ring commutator. All right, instead of a slip ring. All right. So in such a way that if you were to let me do this here. So here would be the induced current. There you go. Induced current here. So if you were to do this, what you would get something like that. I don't know if I can have like nice form with this. Let's see here. No, it doesn't know what to do. Okay, it gives me only, probably Timothy can help me. And okay, so this is where you would get. So with splitting your commutator, a DC generator here, the current will go only in one direction. It will still like go up, because when it's vertical here, this is where it sees the magnetic field changing at the greatest rate. So it'll be like going up and down, going up and down, going up and down. Okay, so that's a DC generator here. Now, yeah, is there a more chat? When does the magnetic field change at the greatest rate? Well, that's how I say here. It's the same idea as this, Manav. Like you see, like my hand going faster here than over here. So the rate at which my hand is moving seems to be faster here than over there. So that's why like the electrical field is greater. Electrical field produced is greater in intensity when the magnetic field, when the rate at which magnetic field changes is greater. We're going to talk about this tomorrow. Okay. I'm not going to get too much in details here, but that's the thing. Okay. Now, does anyone? There we go. Let's do here. Like you guys, like are not curious. Hopefully, you did destroy some motor, perhaps motor that doesn't work anymore. If instead of having if I want the current to be more or less constant, not go like this, does anyone know what I should do in a DC generator? Does anyone have an idea? No? Yeah, Forrest?
You can add more poles.
Yeah. More coils, you mean?
Well, yeah.
More coils? Yeah, that's correct. So, yeah, so what you can do here, you don't have to write this down, but instead of having, so if you've destroyed a little motor that doesn't work, what you would see something like that. Well, it's not as, okay. So here is your coil right here. Okay. And then as it turns, you remember when it's vertical here, it's very, very high. When it's horizontal, it's not so high, right? This is your field magnet right here, right? Field magnet right there. All right. Well, what you can do is instead of having only one coil, why don't you have another coil like this? So what happens here is it happens that when this one is at maximum, this one has no induced current. But when it turns, when this one is vertical now, this one will be vertical. So now the induced current will be maximal. So this is what you do. And if you look at a real motor, you're going to see like coils going one way and then coils going the other way and then coils going at 45 degrees coils. So you keep on doing this here, right? So here you have another one like this, you have another one like this, right? In such a way that at any given moment here, there's always one that will sort of give you the highest induced current. And then when you have this, instead of having only this for one coil, you have multiple one, right? So here, like that would be like a second one, right? That would be like that's what would be for one coil here. For this one, it will be for this one here, will be shifted, right? And then you put another one and another one in such a way here that with time, what you get is only this, right? So the current here will stay like more or less the same. So when the induced current is very high in one, it's going to be low in another one, okay? So this is how they make like a DC generator where the current is virtually like constant by putting more coils at different orientation. Guys, I encourage you, like just go. If there's something like that as a motor and doesn't work, like break it and have a look at it. You'll see like this coil, like copper wires here. You're gonna see like going one way and then another one going the other way and at different angles. So it goes. Pretty neat, huh? Okay, all right. So so you have like some assignment here, some questions you have to work on. I did put on the website like some diagram, some questions. Like there's one page here. You have to draw, right? You have to write your answer on it, but I don't want you to do it in the textbook. So I offered you like a copy to make a copy of this, print it, and then do your just write your solutions on this paper directly. Make sure it's in pencil because if you made a mistake, you need to erase. Okay. And then there's another package to download for tomorrow. Okay. Okay. Questions? All right. So I'll see you tomorrow at 2:30 because it's Wednesday. And so do your homework here. It's not too long, right? It has to do with Lenz's law, of course, electromagnetic induction. And then tomorrow we'll almost finish like the, probably will take like probably by the end of this week, we might be finished with electromagnetisms, right? Or very close to it. Okay. So questions? All right, good. All right, so I'll see you tomorrow and take care.
Thank you, sir.
Bye-bye. Bye.
Hi, sir.
Yeah.
Thank you, sir.